Hi, welcome to lesson 13C, the angle between two lines. The goal of today's lesson is to learn how to determine the angle between two lines in 2 dimensions and 3 dimensions. So a little while ago, we learned about vectors and we learned about how to find the angle between two vectors, and they were positioned tail to tail like this, vector u and vector v. And we learned a little bit about the dot product, and we learned that the dot product, or the scalar product, was equal to the magnitude of vector u multiplied by the magnitude of vector v multiplied by cosine of the angle between them when they're positioned tail to tail. Then if we rearrange this and we divide it by the magnitudes, we would get the cosine of the angle between the two vectors, and then obviously by doing the inverse cosine of both sides, then we would find angle theta. So that's all fine and good, and we've done that with vectors. Now we're going to do that with lines. The issue with lines, though, is that lines go on forever in both directions. If you're talking about a strict definition of lines. And so when we have lines, obviously there are 4 angles to choose from, 2 of them, or there are 2 pairs of equal angles. And so what, for convention, we're going to do is just, if we're trying to find the angle between 2 lines, we'll find the angle between, or the acute angle between the 2 lines, just for simplicity. If we really want to find the other angle, then we just know that this is the supplementary angle to that, and henceforth we just have to subtract the angle that we find from 180. So we'll use the acute angle more specific, well, maybe not more specifically, but just for fun, to make things easier anyways, because we know that the cosine of an acute angle is positive. So we'll just keep things positive and we'll find the cosine of acute angles. If we have 2 lines, and we've got line 1 here equal to, R1 equal to A1 plus SB1, for example, and we've got line R2 equal to A2 plus TB2, then we know that R1 is parallel to R2 if the direction vectors, if there's some constant, a scalar multiple of the direction vectors. So if the 2 direction vectors can be equated with a scalar multiple, then that means that the 2 lines are actually parallel. If, for example, the 2 lines are perpendicular, then we know that the dot product between the 2 direction vectors is 0. So that is basically all we need to know about finding the angle between 2 lines. We're going to be looking at a few examples in class tomorrow, and then we're going to allow you a bit of time in class to work on some practice problems from section C. So take a look at these questions, and then you'll see what's in store for you for tomorrow. And until then, thanks for watching, and we'll see you in class. And just before I let you go, let's move on to section 13D, constant velocity problems. So just very briefly, we know there are lines in space and on planes. So if we have some line where we go from point A to point R, those are 2 points on the line, for example, and they are some distance from a point of reference, say the origin, then we can state that if there's an object that is at initial position A, it has a position vector of A, vector A, and it moves with constant velocity B, it moves in this direction, its position at any time t is given by vector r equals vector a plus t vector b, where t is greater than or equal to 0 because time cannot be negative. So this is basically the direction vector, or it is the direction vector. This is the position vector of a specific point on the line. This is any point along the line, the vector to any point along the line, or the position vector to any point along the line. At this moment, it happens to be pointing at point R. And this is the direction vector. The speed of the object is actually the magnitude of the direction vector. And so that's what we're going to be working on tomorrow after we look at the angle between lines. So again, thanks for watching, and we will see you in the class.